Pluto, the perplexing bantam planet. Living at the external compasses of our planetary group, Pluto is working up further inside the galactic local area. Ongoing reports indicate a potential encounter with Neptune, raising worries among researchers and space fans alike. Prestigious specialists, including Neil deGrasse Tyson and Michio Kaku, have sounded alarms about the possible results of the divine conflict. Yet how did Pluto end up on a crash course with its far-off neighbor? And how could this grandiose crash affect us here on Earth? We should investigate this unfurling event. Once viewed as an undeniable planet, Pluto was subsequently renamed as a bantam planet because of its novel orbit. In spite of this change, it continues to enthrall and draw in stargazers. Ongoing forecasts from conspicuous researchers feature a stressing vicinity between Pluto's path and that of Neptune. These specialists warn against a possible impact between the two planets, representing a significant danger. Pluto's journey around the Sun is marked by its unmatched qualities within our nearby planetary group. Its orbit traverses about 248 years, and since its discovery in 1930, Pluto has yet to complete a full revolution. Adding to its intrigue is the highly elliptical state of its orbit, a departure from the nearly round orbits of the major planets. Furthermore, Pluto's orbit is inclined at 17.18 degrees to the ecliptic plane, making its path more extreme compared to other planets. One prominent feature of Pluto's orbit is its convergence with Neptune's path. For roughly 20 years in each orbit, Pluto approaches closer to the Sun than Neptune. During these periods, Pluto defies expectations based on their respective positions in the nearby planetary group. So why hasn't an impact occurred between Pluto and Neptune? The explanation lies in the gravitational effects exerted by other planets. The assessment of Pluto's orbit commenced shortly after its discovery, presenting a perplexing trajectory for astronomers. Unlike most planets whose orbits align relatively close to the ecliptic plane, Pluto's distinct features include a steep inclination and an elliptical shape. The mystery deepened with the realization that Pluto's orbit intersects that of Neptune. The stability of Pluto's orbit amid these complexities serves as evidence of the intricacies inherent in space mechanics. The three-body problem in space involves understanding the movement and gravitational interactions among three celestial bodies, such as Pluto, Neptune, and the Sun. This problem explains the complex exchange of their paths and gravitational influences. Terms like orbital precession, inclination, vibration, and the Chi mechanism contribute to unraveling the celestial puzzle. Astrophysicists state that orbital precession, responsible for maintaining planets in their orbits, plays a crucial role in the case of Pluto and Neptune. This term means that when Pluto intersects Neptune's orbit, it is positioned no less than 90 degrees away from Neptune, critically preventing potential collisions. Inclination and libration ensure that when Pluto approaches Neptune or other giant planets, it is positioned significantly above their orbital plane, providing an extra layer of protection against impacts. The Chi mechanism explains why Pluto's orbit around the Sun appears unusual but remains stable over the long term. Despite apparent irregularities in space, numerical simulations in the late 1980s revealed that, despite stable properties, Pluto's orbit is indeed turbulent. Minor initial deviations lead to significant changes over millennia. Nonetheless, Pluto's unique orbit maintains stability over extremely long timescales, keeping chaos at bay. Recent computer simulations have enhanced our understanding of how giant planets like Neptune, Jupiter, and Saturn impact Pluto's path around the Sun. Neptune's peculiar relationship with Pluto, completing 3 orbits for every 2 of Pluto, contributes to the stability of Pluto's orbit. Furthermore, Jupiter's immense gravity exerts a significant influence, while Saturn's effect, though smaller, also plays a role. Through comprehensive studies, researchers have demonstrated that the combined effects of Neptune, Jupiter, and Saturn ensure the safe and stable movement of Pluto in space for billions of years. These phenomena are crucial for maintaining the stability and consistency of celestial movement in the universe. Understanding Pluto's orbit is especially vital amid discussions about a potential collision with Neptune in the future. This knowledge provides a clearer understanding of the dynamic nature of the nearby planetary group. Pluto's case highlights how seemingly unstable orbits can achieve balance through the complex interplay of gravitational forces and orbital mechanics. Continuous observation and analysis of these phenomena are essential for gaining a better grasp of our place in the universe. Exploring the depths of space often reveals the unpredictable nature of celestial bodies, and Pluto's orbit serves as a perfect example of this unpredictability. The concept of orbital chaos strikingly illustrates the sensitive dependence of a celestial body's path on its initial conditions, as demonstrated in Pluto's case. Even slight variations in the dwarf planet's position or speed can significantly alter its long-term orbit. Virtual simulations have been instrumental in helping researchers understand how Pluto moves in space. By making small changes in these simulations, astronomers can observe how minor adjustments can have a significant impact on Pluto's trajectory. In the late 1980s, these simulations revealed an intriguing aspect of Pluto's orbit. Despite factors like orbital precession and inclination contributing to its stability, Pluto's orbit can still display irregularities. Even a tiny initial difference in Pluto's position or speed can lead to substantial changes in its path over many years. Despite this inherent disorder, Pluto's orbit remains stable over an extraordinarily long time span, extending over billions of years. This suggests that beneath its seemingly erratic appearance, Pluto's journey around the Sun follows an organized order. Predicting cosmic events, particularly with planets like Pluto that have erratic orbits, is very challenging. The inherent unpredictability of these systems makes long-term forecasts difficult. Numerical simulations help us understand and anticipate the future paths of celestial bodies, but they also reveal the limitations of our predictive abilities. These models heavily rely on precise initial conditions and simulate complex interactions. Even a small error can lead to vastly different outcomes, making accurate predictions challenging. The chaotic nature of celestial orbits, such as Pluto's, reminds us of the ever-changing universe. While we've made progress in understanding space, Pluto's case underscores our ongoing limited knowledge. Understanding the gravitational effects of giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the planetary group. It demonstrates how each planet's presence and position can influence the stability and trajectory of other bodies in the system. Despite these complex forces, prominent astrophysicists are expressing concerns about a possible collision between Pluto and Neptune. This raises questions about why such a collision, which seems unlikely given these complex dynamics, is now a subject of concern. Neil deGrasse Tyson, a renowned astrophysicist, presents an insightful perspective on the mysteries of our planetary group, especially regarding Pluto. Tyson, known for renaming Pluto as a dwarf planet rather than a full-fledged planet, shares thoughtful insights into how our understanding of celestial mechanics is continually evolving. He views Pluto's renaming not as a downgrade but as a necessary adjustment in line with our growing knowledge about the various objects orbiting the Sun. His approach to celestial mechanics involves ongoing learning and adaptation. He sees the complexities of orbits like Pluto's as a sign of how much more there is to discover in space. Tyson believes that the allure of these questions makes astronomy so fascinating. Additionally, Tyson acknowledges how space-related events and discoveries shape public interest in space science. Pluto's renaming and its unusual orbit are valuable opportunities to capture the public's imagination and interest in astronomy. By exploring the dynamic and sometimes unpredictable aspects of celestial mechanics, Tyson aims to foster a deeper understanding and appreciation for the universe. Neil deGrasse Tyson opens a window for the general public to marvel at the wonders and mysteries of the universe. Working alongside other researchers, Tyson actively alerts the public to the potential danger of Pluto's unusual path. After extensive investigation, he has raised concerns that the three-body problem could pose a real threat, suggesting that a collision with Neptune might be overdue. Furthermore, Tyson emphasizes how such a collision could disrupt the equilibrium of the universe and lead to catastrophic consequences extending to Earth. A collision between Pluto and Neptune would be an extraordinary and catastrophic event in our planetary group. This impact would release a massive amount of energy, potentially shattering Pluto due to its small size and icy composition. Debris from the collision could scatter across the planetary group, posing potential hazards to other planets and their moons. For Neptune, such an impact might potentially alter its atmosphere and orbit, depending on the specific details of the collision. Michio Kaku, a notable theoretical physicist known for his work in string theory and science communication, offers a unique perspective on this scenario. His views on the future of space exploration and the connection between celestial mechanics and theoretical physics provide profound insights into phenomena like Pluto's orbit. Kaku sees the study of Pluto and its orbit as a glimpse into the future of space exploration. Understanding the complex gravitational interactions and orbital elements of celestial bodies like Pluto, according to Kaku, can offer crucial insights for future space missions. This knowledge can aid in navigating the planetary system more effectively, predicting potential hazards, and planning missions to the outer reaches of our planetary group and beyond. Kaku emphasizes that the lessons learned from studying Pluto's orbit can be applied to exploring other celestial bodies, providing a framework for approaching and understanding distant worlds. In examining planetary physics, Kaku often highlights the deep connection between celestial mechanics and theoretical physics. He believes that the movements and interactions of planets, such as the gravitational dance between Pluto and Neptune, are not isolated events but are connected to fundamental principles of physics. Kaku's work in theoretical physics, particularly in string theory, aims to grasp these principles at the most fundamental level. He proposes that studying the complexities of celestial mechanics, like Pluto's orbit, can yield insights into the underlying laws of the universe. Like Tyson, Kaku has also addressed the potential impact, relating it to his theories about the universe. If Pluto and Neptune were to collide, it would be a significant event in astronomy. Further exploration of Pluto's unique orbital dynamics. To delve deeper into the peculiarities of Pluto's orbit, it's essential to understand its interactions with other celestial bodies. The orbital dynamics of Pluto, while stable over long timescales, reveal intricate details about the nature of gravitational interactions in our solar system. One interesting aspect is Pluto's relationship with the Kuiper Belt, a region of the solar system beyond Neptune that contains numerous small, icy bodies. Pluto is considered one of the largest members of this belt, and its orbit takes it well into this region. The Kuiper Belt's influence on Pluto's orbit cannot be underestimated. The gravitational pull from other Kuiper Belt objects and the overall mass distribution in this region can introduce subtle perturbations to Pluto's path. These perturbations can affect the orbit's eccentricity and inclination, though they do not generally lead to dramatic changes in the long term. Nevertheless, these interactions are crucial for understanding the full scope of Pluto's orbital mechanics. Furthermore, Pluto's orbit is also influenced by its relatively large moon, Charon. Charon's gravitational influence contributes to the stability of Pluto's orbit in a few ways. The Pluto-Charon system is unique due to its barycenter, the center of mass around which both Pluto and Charon orbit, being located outside of Pluto itself. This mutual orbit creates a significant gravitational interaction between the two bodies, which can affect Pluto's trajectory and its interactions with other planets. In addition to Charon, Pluto has 5 smaller moons: Styx, Nix, Kerberos, Hydra, and a 5th moon discovered more recently. Each of these moons exerts a small gravitational force on Pluto and Charon. Although these effects are minimal, they add layers of complexity to the overall gravitational dynamics of the Pluto system. Studying these moons provides valuable insights into how even small celestial bodies can influence their larger counterparts. One of the key tools for understanding Pluto's orbital dynamics is observational astronomy. The use of telescopes, both ground-based and space-based, allows scientists to track Pluto's position with high precision. Observations from the Hubble Space Telescope, for instance, have provided critical data on Pluto's orbit and its interactions with other objects in the solar system. This data is essential for refining models of Pluto's orbital behavior and for predicting future positions. The study of Pluto's orbit also involves complex computer modeling and simulations. Astrophysicists use numerical simulations to explore various scenarios and potential outcomes of Pluto's interactions with other celestial bodies. These models incorporate a wide range of factors, including gravitational influences from all known planets and major moons, as well as the effects of perturbations from other Kuiper Belt objects. Simulating these interactions helps researchers predict possible future changes in Pluto's orbit and assess the likelihood of potential collisions. As we further investigate Pluto's orbit, it becomes apparent that understanding the dynamics of such distant objects requires a multidisciplinary approach. Collaboration between observational astronomers, theoretical physicists, and computational scientists is crucial. Each discipline provides different insights that contribute to a more comprehensive understanding of Pluto's place in the solar system. Recent advances in technology have enhanced our ability to study distant celestial objects like Pluto. The New Horizons mission, launched by NASA, has been instrumental in providing detailed data about Pluto. In 2015, New Horizons made a historic flyby of Pluto, capturing unprecedented images and data. This mission has offered new perspectives on Pluto's surface, atmosphere, and moons, and has greatly expanded our knowledge of this distant world. The data from New Horizons has led to numerous discoveries, such as the presence of a complex and varied surface on Pluto. The planet exhibits a range of geological features, including vast plains of frozen nitrogen, towering ice mountains, and deep canyons. These features are crucial for understanding the geophysical processes at work on Pluto and how they might affect its orbit and interactions with other objects. Pluto's atmosphere is another area of significant interest. The New Horizons mission revealed that Pluto has a thin, layered atmosphere composed mainly of nitrogen, with traces of methane and carbon monoxide. The dynamics of this atmosphere, including its interactions with the solar wind and its response to changes in Pluto's distance from the Sun, play a role in shaping Pluto's surface and its overall orbital behavior. In addition to its direct influence on Pluto, the study of this dwarf planet provides insights into the early solar system's formation. Pluto and other Kuiper Belt objects are considered remnants from the early solar system, preserving clues about the conditions and processes that prevailed during its formation. Analyzing these objects helps scientists piece together the history of our solar system and understand how the planets and other bodies came to be. Looking forward, there are ongoing efforts to explore more of the Kuiper Belt and beyond. Future missions could further enhance our understanding of Pluto and similar distant objects. These missions may involve advanced spacecraft capable of traveling to and studying other Kuiper Belt objects, offering new data that could refine our models of Pluto's orbit and its interactions with the solar system. In summary, while Pluto's orbit is stable over long timescales, its dynamics are influenced by a complex interplay of factors, including gravitational interactions with other celestial bodies, perturbations from the Kuiper Belt, and the presence of its moons. Observational and computational tools continue to provide valuable insights into these interactions. The ongoing study of Pluto and other distant objects helps us better understand not only these individual bodies but also the broader dynamics of the solar system. Future explorations and technological advancements will likely continue to shed light on the mysteries of Pluto and its role in the cosmic landscape.